Well, I'm going to talk about another non-polarizing topic in climate change. So Ned mentioned yesterday when he had his salmon talk about how there are some risk factors that we're kind of trying to get a handle on about how climate change is going to potentially impact stream flows, how it might impact stream temperatures, and how it might impact sediments. And so we had the good fortune of the Nooksack tribe providing us funding to try to address those three topics. So we're in a series of projects. What I'm going to share with you today is kind of the first set of that projects, which is the work of my graduate student, Ryan Murphy. And I just want to make a comment about the reason I have an opportunity to provide this science for you today is because of the good fortune I've had of exceptional graduate students in the past who have been able to provide all this work for you. So it's really off the backs of my graduate students that I want to share this kind of information today. So Ryan, I did have collaborators with the University of Washington, provided some of the data sets and some information about the glacial models. But Ryan is now working as a climate scientist for the Point No Point Tribal Council, doing the same types of modeling in the Olympic Peninsula. So if you want to follow his work, I encourage you to do that. So the basin, you're well aware of, we're dealing with the upper basin. We broke it up into three different drainages, just so we could assess the difference between, for example, glaciated basins versus non-glaciated basins. What we're looking at here is about 1,500 square kilometers. About 70% of that is above 500 meters, meaning, and the reason I mentioned 500 meters because that's about where that kind of rain snow threshold currently exists right now. It has about 3,400 hectares of ice that are currently exposed to the elements. And what's unique about this basin, and all you're aware, it's very typical.
Sorry to interrupt. We need to move the mic up just a little.
I'm a little taller.
Yeah,
sorry.
You're a little taller. Yeah.
But the reason this basin, like all the Pacific Northwest basins, it's what we call as a transient basin. It's very sensitive to that kind of increasing warming temperatures because of that rain snow threshold. For you skiers out there, you realize it can be raining at Mount Baker ski area one day and snowing the next. So it's very sensitive to any kind of warming climates. So our objective then was for this study, was to kind of look at how will warming climates impact predominantly stream flow, which is influenced obviously by the snowpack and the glacier contributions up in the Nooksack. The only mechanism by which we can look into the future, obviously, is through numerical modeling. So we're using the best available tools for that. And what we're doing is taking climate data, we're forcing that into the basin and using numerical models that then try to simulate how the basin is going to respond to that throughout the 21st century. So we're going to be looking at the data I'm going to show with you today is snow water equivalents. We're going to look at glacial dynamics and obviously the influence on stream flow both of those have. I'll show you the slide a couple of times, but just kind of a guide for me to guide through the talk. Obviously, we need to set up the model. Let me tell you a little bit about the model and the meteorological data sets that we're going to be using to force the model, and then we'll march through the setup. So the model itself, did I miss a slide? I'm going to go back here. I don't know if I can go back. I missed this slide. So the model that we use was developed at the University of Washington Pacific Northwest Lab. I've been using this for about 15 years. In fact, the first graduate student who applied this model is going to be giving a talk this afternoon, Jake Chenault. He was one of my first graduate students to use the DHSVM, and he actually looked at the impact of climate on the Thunder Creek Basin in the North Cascades. So what's unique about since Jay used that model, what's unique about it now has a glacial dynamics component to it. So there's a research group at the University of British Columbia that eventually, and it was developed this glacial model that was integrated into the DHSVM, and that's how we work with the colleagues on the University of Washington. We work together on trying to apply this to the Nooksack Basin. So if you want to learn a little bit more about that model, I do have links. Most of these, I can't digest all this information with you in a 15-minute talk, so I do have links that you can learn more about this as you proceed through the PowerPoint. So the physics of the basin are all driven by inputs, grid inputs. We're using 50-meter grids to simulate this. So all the hydrologic processes you can think about that drive any kind of surface hydrology where you're talking infiltration, percolation, groundwater flow, evapotranspiration are all driven by grids. And these are the grid inputs. These are processed in ArcGIS and used to define that kind of spatial characteristics of the basin. Now, I have one slide here on calibration, but I'm going to tell you that the calibration process of the model is probably the most onerous component of the modeling process. So it's and especially with the glacial dynamics model, so what we're trying to do is we alter temperature lapse rates, precipitation lapse rates, the inputs of the data, all the elements that are driving the dynamics and physics of all these processes, and we're trying to compare those to observed data until we get some kind of reasonable match. Now, we were able to nail the stream flow really well, and the snowpack we were able to calibrate reasonably well as well. There are certain basins, the South Fork, and I think Susan Dickerson will validate that. It's a tricky basin to try to calibrate to. Where we had some issues in the calibration actually was in the glacial model. So we were actually producing more, because of the way the DHSVM simulates the lapse rates, you can't control lapse rates at really high elevations. So we were producing a little bit colder temperatures than we anticipated, which gave us some thin ice coverages that wasn't real. But we couldn't resolve that. So some of the results I'm going to show you, I'll comment about how that did impact the stream flow. I want to mention this too, is that another unique attribute about the trend of this numerical modeling in the past 5 years is using what's called gridded data sets. So the data here, each one of these red dots in a sense represents a weather station. And there are institutions, primarily at the University of Idaho, that have statistically processed data that observed from the landscape and generated time series at each one of these grid points. So essentially, they cover the entire United States. So we take these grid sets and we further process them into the inputs we require for the DHSVM. So you can imagine now, each one of these red dots contains a time series that's 3 hours for about 90 years. So we can go back historically for 90 years on this. So each one of these has by a 3 hour time steps has a temperature, a precip, a wind speed, a humidity, shortwave radiation, longwave radiation, which are driving all the physics of the processes. It does serve also as a calibration process because naturally if it's statistically derived, there's observational problems, and we have to go in and what's called bias correct some of these variables until we achieve a calibration that gives us reasonable results. So that's also part of that calibration process, is actually manipulating the metadata that's feeding into the model. So once we fully calibrate the model, we're satisfied with what historical stream flows look like, we're satisfied with what the historical snowpack looks like, we're satisfied somewhat with what the glacial extent looks like. We're then at the point of saying, all right, let's feed it some futuristic data and see how the basin responds to that. Now, remember, there's a caveat to that. We're assuming that the basin is the physics of the basin is going to stay the same throughout the next century. So that's one caveat about understanding what we're going to be producing in terms of the future, right? So the futuristic data, there's a couple things I want to point out about this. The climate models data that we're using, there's institutions all over the United States that are generating what that future climate might look like. And they're using different what we call narratives or scenarios to kind of project how warm it's going to be in the future and what that precipitation might look like in the future. So terms I'm going to be using is a GCM, which is a global climate model. There are narratives that are used in those models to kind of address where we're heading in terms of our future warming events. What I mean by that is that let's say we start today and we choose to do nothing about CO2 discharges into the atmosphere. Continue on the status quo. That's a narrative. Okay, and that would be the most aggressive narrative here. This is going to be worst case scenario. Population grows, we continue with industries, we keep dumping CO2 in the atmosphere, and it's going to continue to get warmer. So I'm going to be showing you results from this narrative. It's the worst case scenario narrative. There's another narrative that says, all right, let's say we take in some political action, we decide to impose mitigations on discharges, and we're trying to do the right thing. We're going to be producing less CO2. That's going to be a narrative that's going to be somewhere down here. So I'm using two different narratives, kind of a worst case scenario, something a little less conservative. So the point I'm going to make here too is that even if we decide to make changes today and keep continuing making those changes, it's going to take decades for those to take place. So you can tell, like, it takes till about 2050 for those to really spread apart. And the climate models that I'm going to be dumping into the DHSVM have a range from 2 degrees sea warming over the next century and 4.7 degrees warming over the next century. So one of the attributes of these global climate models, and this is one step I need to kind of explain as well, is that the grid scale that they're produced at are very large. Meaning this is a grid cell of a global climate model. And they're saying, all right, it's going to get warmer by a certain degree in this cell. So what part of the data processing that has to take place is called downscaling. You have to take that warming trend and map it on to the historical data. So in this case, the historical data happens to be these little red dots. And each one of these red dots, we're using 20 different climate scenarios. So we have 10 associated with the RCP 4.5, 10 associated with the RCP 8.5. So each one of these red dots, which is a MET station, now has downscaled data. Each one of those, the red dots, has 100 years worth of data at 3-hour time steps. 20 different scenarios. So the goal then is to take those data sets and feed those into our calibrated model and then actually observe what is going to be the response of the basin. Obviously, there's a lot of uncertainty in this. So the data results I'm going to show you are trends. They're not, I can't tell you what the flow is going to be on May 1st in 2051. I can tell you what the trends are going to be. Okay? Just for your information, how computationally intensive this is, one of those time series, so we run a 100-year time series, one model run in the North Fork takes 6 days to run. And we run 40 of them in the North Fork. We had to run 40 of them in the Middle Fork and 20 of those in the South Fork. We're now working on a cluster in the CS department that allows us to be much more computationally efficient about these. We can run 60 models at once. But when Ryan was doing this work, we had 3 boxes and we're running, running these things for weeks. And the data processing associated with that is intensive as well. So what I'm going to show you are results now that are revolved around certain years in the future. So, for example, when I show you dates 2025, when I show you dates 2050, when I show you dates 2075, these are 30-year windows surrounding those dates. So we think of climate as being kind of a 30-year average of weather. So that's why we're looking at the results. So when I show you these dates, it's not what's happening at 2075, it's what's 30 years surrounding that year of 2075. So here are some results of the potential future kind of areal and thickness of ice around Mount Baker, Mount Shuxton. This is actually, believe it or not, this was actually 2050, not the year surrounding 2050. So what you're looking at here is an aerial average of 20 different scenarios and taking the average of the aerial coverage of that ice. So this is for the 4.5, this is for 2099, 4.5. This is 2050, 8.5. You can see there isn't much difference between these until you get later in the century. So there's a lot less ice. There's about 85 to 90% less ice projected to be occurring on Mount Baker by the year 2099. An outcome of that, not only is that going to influence flow, but that's also going to influence, as mentioned by Ned yesterday, the sediment. As these glaciers recede back, they melt, they're harboring a lot of sediment. What is that going to mean in terms of delivery of sediment to the streams? How is that going to impact fish? Let me explain. I'm going to show you a number of these types of plots. So I want to take an opportunity to just explain it just for a minute. See, these gray lines here represent a single GCM. So there are actually 20 light gray lines there. 10 associated with the RCP 4.5, 10 associated with the RCP 8.5. A dot on that gray line represents an average of 30 years for a particular date. So it's a daily average. The blue lines and the red lines represent the medians for those respective RCPs. Notice this black line here is the historical modeled meltwater coming off of glaciers currently. So the black line here is the same position in each one of these plots. Notice how much more water is projected to be produced by that melting glaciers in the next 10 years. This is because of that extra ice that the model produced in the calibration process. So I don't really believe this. There will be more meltwater produced in the next 2 decades because you're going to be exposing a large surface area of ice, and that's going to be exposed to warmer temperatures, so we will see more water moving into that. I didn't see any numbers put up there yet. 1 minute. So let's go to this here. So this is the projected snow coverage, all right? So the light gray, the light blue here represents historical snow coverage, averaged over 30 years. The darker colors represent what that snow coverage is going to look like in the decades to come. Again, around 2075. Imagine now, decades from now, when this light area now is exposed to rainfall rather than snow and its impact on sediment. So Eric Grossman's going to speak to that. One of my graduate students, Kevin Knapp, is working on how that's going to impact sediment to the streams. Also, how is this snowmelt going to impact temperatures? Let's look at stream flow. This is at the Cedarville gauge. This black line represents historical flows. The blue lines and the red lines are the trends you want to take a look at. So what we're producing here, what we're predicting is this is all spring runoff. This is all spring snowpack, meltwater. Since there's going to be less snow melting, there's going to be less spring snow runoff or meltwater. So you can see around 2050, 2075, there's a huge increase in winter rain, right? Which is going to be increasing winter stream flows, which is going to be increasing sediment to the streams. And then a dramatic decline of spring runoff, and there's going to be an even more dramatic decline in summer flows. The question we have to think about that from a water resource perspective is just water quantity, but also how it's going to be impacting fish habitat. I put this, so I'm going to close with this one. Remember the dry year we had, 2015? Here are the actual stream flows for that year. Remember all the comments we were thinking about, well, this is what we're going to be thinking about what climate change is going to look like, right? So what we saw in 2015 is totally kind of mapping what we're projecting in the future. I'll end with this, I guess. This, the PowerPoint's available. You guys can go and look at this in more detail, but this is from Susan Dickerson's work, who did original climate change modeling in the Nooksack. And all I'm going to say here is that there's going to be an increase in peak flows. I think there's going to have to be a lot more work done, and that's kind of our next research agenda is what are the peak flows going to be looking at, and it's going to take a little bit more assessment, I think, to nail that to the degree that's given here, but this is kind of a first assessment, I would say a first order crack, where you know there's going to be an increase in peak flows. How is that going to impact flooding events? How is it going to impact it, stream geomorphology, et cetera, but that's going to be kind of work in the future. Can I end with one? This is a cool little simulation here. So Ryan put this together. This is how the glaciers who are responding. These are 10-year averages. So remember, you're looking at 20 different climate change scenarios that are averaged into one image, and then we spit that out every 10 years. So this is how the glaciers will potentially be responding. And again, I want to point out, how is sediment related to that? How are stream temperatures going to be related to that? And I have 2 current graduate students right now, one who's looking at the assessment of this on stream temperatures. We should have her thesis done, I would say, in the next few months. And Kevin Knapp, another graduate student of mine, who's looking at how is this going to impact stream sediments, and he should be done in a few months as well. And we're just starting a similar project in the Stillaguamish Basin. So we're getting funding from the Stillaguamish tribe to continue this work in just south of us here.
Yes, I have one quick question, if I could, in that 3-minute time. The 2015 anomaly is attributed to perhaps some oceanic conditions and a global climate shift. Is the assumption that past historical records that you're using for meteorology capture that? Can you have shifting states, so to speak?
Right. We can't predict how, when I'm saying that these warming climates are mapped onto historical data, so the historical data captures all the PDOs and El Niños and all these kind of climate trends that we've been seeing over the past number of decades, right? That's a caveat of the model. We're assuming those same trends are going to continue into the future. So we don't know how the actual climate shift will influence those weather patterns and where they're going to be seeing the same types of phenomena. So that's a caveat of the model, is that we can only project based on what we've seen in the past. It's a good question.